Hi everybody. When it comes to analyzing how good our code is running, we care about two things. How fast is it running, as in can it be done in a very small amount of time, and how much space does it take up, or how much memory does it need to fully accomplish its task. To talk about these two things, we need a consistent way of representing it, especially when we're talking to other people about comparing which code is better or analyzing its performance in a very mathematical way. And to do that, we have this thing known as the Big-O notation, and we're going to learn all about it in the next few minutes. So to help us better understand the Big-O notation, we can spend a lot of time giving you the rundown of its history and all the mathematical things behind it, but I think it'll make more sense to start with an example. So in our example, we have some code that checks the number of digits that a particular number has. So in this case, we have the number 3,415, 3, 4, 1, and 5. How many digits are present here? So one way of doing this is that we start at the left and we say 1, 2, 3, and 4. So this number has 4 digits. Let's go with a slightly larger number. In this case, 241,359. Same approach. We start 1, 2, 3, 4, 5, and 6. This number has 6 digits. Now, what we can kind of see here is that the number of times we count to see how many digits there are is directly related to how big of a number we're dealing with. Earlier number was 4 digits, so we had to count 4 times. In this case, our number is 6 digits long, so we have 6 degrees of values to focus on. Now, the way to think about it is the number of steps is directly proportional to the size of our input. And if we had to actually graph this out or plot this, you can see that on the x-axis we have the size of input, and the number of steps required, in this case counting each digit, is on the y-axis, and it's a straight line. The larger a number, the more steps are required to count how many items there are. Now, for this particular example, where it's a one-to-one mapping between amount of work we do versus how big of the item we're dealing with, this is an example of linear growth. And there are many terms like this you're going to see, like linear and constant, quadratic, logarithmic, and things like that. And we'll get there in a few moments. But let's look at one more example. Let's say that we have some code that tells us whether a number is odd or even. And let's say our input numbers look a little bit like this. We have some large numbers like our 241,539 from earlier, some small numbers like 246, and we have all these numbers here. To calculate whether a number is odd or even, there's a simple approach we can take. We just look at the very last digit in the case of the numbers and then quickly determine if it's odd or even. In this case though, right, the thing to keep in mind is it doesn't really matter how large our input was. It doesn't matter how large the number was. All we really cared about was the least significant digit and integer, and then make sure that it is either odd or even. And so in this case, the number of steps required versus number input size is constant. It doesn't matter how much work we do. We do a constant amount of work, which is could be a lot, could be small, but it's the same number. And the size of our input, the size of our number changing, doesn't change things at all. This is an example of constant growth. Now, where does Big-O notation fall into all of this? There's an old expression that you've probably heard from TV or books or from family members, and that is really, don't sweat the little details, focus on the big things. The Big-O notation is really the mathematical embodiment of this phrase, because when it comes to analyzing the performance of our code and how our algorithms are running, there's no shortage of little details we can get caught up on, and those details often aren't really important. They're important at a very micro level, but in the big picture of whether something is running efficiently or not, they don't matter. And what really matters is how much work our code does relative to the size of our input. That's really it. Whether it is extra in the same amount or a fraction of that amount, doesn't matter. It's just really the overarching thing, and that's where the Big-O notation comes in. Now, a formal definition of the Big-O notation is that it is a mathematical way to represent the upper bound or worst case scenario of how our code runs for a variety of different inputs. And so here's the way Big-O notation is represented. Earlier, we saw an example of the chart of linear growth. We saw the size of input, steps required, and we saw the line was increasing in a one-to-one mapping. The way we would represent that is not through a chart in many cases. We would use what's known as this Big-O notation, which, as you can tell, it has literally a big O, like a capital O, some parentheses, and a value inside it that indicates the rate of the growth. In this case, our number is linear, the growth is linear, so we just use n to signify that it is linear. And now, The O in Big O isn't just there because it looks cool, it's actually there because it stands for order of, and it represents the growth rate of our algorithm. And growth can be in terms of, to echo what we talked about earlier, in two things. It could be time, how quickly does my code run, or space, how much memory does it really take up. The n argument that we saw earlier, mentioned, I said it was going to be for linear. The value specifies what type of growth you're going to be seeing. So examples would be, in this case, O of 1 would be constant, O of log n would be logarithmic growth, O of n is linear, and then you have multiple variations of it. And we'll look at how these actually look when plotted to give you an idea of the relative amount of work that needs to be done compared to the input that we are dealing with. Now, the important part about, when I said don't sweat the details, is that with Big O, we don't worry about the modifiers. We don't worry about the exact rate at how the big numbers are going to be modified. So in this case, using a linear case as an example, when we analyze our code, we're going to have very precise ways of getting very specific in how the code is going to handle various edge cases, how it's going to handle various scenarios where the growth can be very specific in how we define it. But with Big O, it doesn't matter. It doesn't matter if our growth is O of 2n or O of n plus 5 or 4n minus n minus 2, n over 2. These are all absolutely mathematically valid, but from a Big O point of view, they're all linear. They're all just Big O of n. And so in other words, it may seem like going from, in this case, I plotted two values, the growth for O of n and O of 2n. It may seem like going from O of n to O of 2n is a huge, big value change, but it really isn't, because when we zoom all the way out and talk about really large input sizes, this difference will be trivial. And it's especially true when we look at what some of the other values of n can be. And here's where it really becomes interesting. We can actually visualize the growth of n. And here you can see that, we had to classify algorithms sort of fast, average, and slow, which is how you'll typically see algorithms defined in many scenarios. You can see the fast algorithms are, in this case, the constant time, determining whether a number is odd or even, or O of log n, where the growth is logarithmic, where, there's going to be it's kind of an accelerated growth at the beginning, but then as your input size gets larger and larger, the actual growth doesn't scale quite as much. So you can see it kind of peters off at the very end. Average is linear, or n log n, and those are both the examples that we'll see many algorithms about later on. And the slow ones are ones where algorithms doing a lot of work relative to the size of the input. You might have a minor change in the size of your input, but that results in a much larger disproportional rate of growth in the work that you do. And those are like your n squared, 2 of n factorial examples. So exponential, polynomial. These are the kind of things that you want to avoid, but sometimes they're unavoidable. You just have to know how to deal with them. Now, before I wrap things up though, in many formal textbooks, you may even see other notations. You may see big theta, you may see big omega, and all of these other, Greek symbols. Some of them are even lowercase symbols, for example. The two more common non-big O notations are big theta, which means average case scenario, and big omega, which represents the best case scenario. So it's good to sometimes keep that in your back pocket if it comes really handy. But there you have it though, the big O notation. It's a mathematical notation used to describe the upper bound or worst case scenario of a code's time or space complexity. Now, to get all mathematical on us, it provides an asymptotic upper limit on our code's growth rate. By using the Big O notation, we can talk about code complexity in a way that is universally understood, and it is pretty consistent. And it's important because it allows us to analyze and compare the efficiency of different coding approaches. And it kind of helps us to echo what we talked about with our data structures earlier. It helps us decide what trade-offs are worth making given the context our code will be running in. So if you enjoyed this content, you'll probably enjoy my book, Algorithms, Absolute Beginner's Guide, available in paperback and Kindle editions and other digital forms, where we look at how to map the right algorithm with the right data structure and do it so in a way that is efficient. So you're going to be well prepared for what lays ahead in computer science or programming or anything else you decide to do. And of course, learning data structures and algorithms and things like Big O notation, it's much easier and more fun with a group of people. And so there's a large community at formnetgroup.com, link below, check it out and be a part of it. And of course, picking up links, you'll find below this video or tagged with this video, links to all the resources that can help you not just better understand how to understand Big O notation, but also keep up with all the content that I create. And so with that, I will see you all next time.